All right, let's start this essay. So I kind of got a list here. We're going over all of this: RMPs, Nernst equation, action potentials, some capacitance, and length constant. So let's just start with RMP. So RMP is the resting membrane potential. Okay, so all this is saying is we got a cell, and this inside here is more negative than out here. That's all it's saying. So how this is kind of established is by a few different ways. First, we got a sodium-potassium pump, right? And we have lots and lots of sodium out here, and not that much potassium. Okay, we have not a lot of sodium in here, but we have lots of potassium. So of course we're getting 3 sodium in, 2 potassium in, right? So this potassium wants to leave. It's going against its concentration gradient. So we have potassium leak channels where it wants to go out. And so it will, right? It'll go out, but as you're taking out away these pluses, right? We're bringing them out here. We have a chemical gradient, right? That's our K plus, and we have an electrical gradient. Because as you're bringing this K plus out, it's going to become more negative inside the cell than outside the cell. And at a certain point, this potassium is going to hit a point where it'll, instead of going out, it'll be pulled to the negative side. And so this is what our resting membrane potential is. A lot of times in class, it was about -70 is like that's the one we always talked about. There's other ones, but we're just gonna focus on -70 all day. So this will come out, and at a certain point, it'll get into an electrochemical equilibrium. This won't go out, or as much as coming in will go out, but it can't go out more than that because that's where it's stuck. So that's basically it for RMP. Okay, so let's just do some conditions that affect it. We're going to talk about hyperkalemia and hypokalemia. So let's just make a graph here. I'm going to do it right here. So this is -70. This is where we want to be. We'll just say this is 0. And then this is 30. We're going to use this a little bit later with action potentials. Okay, so so this is where we want to be. We're going, right? And then say we get hyperkalemia. Kalemia is in the blood or outside of the cell. So say we get a bunch more K pluses out here, right? Now this concentration gradient is not so strong, and thus we're going to have less sodium want to come out, making it more positive within the cell. So this doesn't want to go out anymore because, well, we've changed everything. And so now our resting potential is going to be whoop, higher. Okay, we're going to go up higher, and we're going to level off. Now our resting membrane potential is higher. If we have hypokalemia, so that's, say we get rid of a lot more potassium, almost all of it, right? We're going to have a higher concentration gradient than an electric gradient, and thus our resting potential will go down. See that? There's different things that you can do. There's a threshold about at, we're just going to say -50, right? And we'll talk more about this when we talk about action potentials. But just know hypercalcemia and hypocalcemia will lower this either up the threshold or lower the threshold. And that's important to action potentials. Okay, let's get to Nernst equations. Nernst equations, basically we're just saying how much force these want to either leave the cell or go into the cell. So the Nernst equation's right over here. So EX equals negative 61 over z, which is, which would be positive 1 for these, right? That's what z is, so this would be, we're just gonna use NA, right? So positive 1 log of x, so this is basically it's the concentration gradient. So x of inside, so Na, there's not a lot, Na inside, so we're just gonna say, let's just say 20. I don't know, I'm throwing out numbers there. And then, the outside, right, that's the x on the bottom, is going to be, let's just say 300, just because it's super strong. So we do that math, we're gonna get something, I don't have my calculator on me. Anyways, so we're gonna get Ex equals this number, and that is the Nernst equation. So now we're gonna talk about driving force. So driving force, we're gonna have our resting membrane potential, which is negative 70, minus Ex. And that's gonna give us our driving force. So what happens if we open up all of these? What's the driving force of all of this coming into the cell or going out of the cell, right? And that's what this tells us, how much power there is of going out and in the cell. So that would go right there. We get a driving force that's pretty high of it going into the cell, because it really wants to go in there, but it can't. It can only go in so much. Okay, that's it for that. Let's get to, we're gonna leave this here for us, and we're going to go to action potential. So an action potential, first we're gonna talk about graded potentials. So we're gonna make this bigger actually. Make a big old one. Boop, zoom. Okay, so we got our negative 70. Here's our negative 50, dash, 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 dash. And we're gonna say this is 0, and then this is 30. Okay, so we have a resting membrane potential of 70. And say we have a graded potential. So usually this is either mechanical or ligand gated Na+. It could be other things too, but we're just gonna say ligand gated sodium. And what this is gonna do, it's gonna rush in, right? It's a stimulus. This is what graded potentials are. They're stimulus. So you can have a graded potential that would just be like, whoop, you know, pretty simple. You can have graded potentials, but what's happening is it's not an action potential until it hits negative 50. This is what we call our threshold. The threshold is we have sodium pumps, voltage gated pumps, that won't open up until negative 50, okay? So, we have a graded potential. You can have graded potentials that get close but won't open it, okay? But say we have a graded potential that does. So we go, boop, we hit this. This is our threshold. This little voltage gated pump reacts. It's gonna open up. And then we're gonna have a flood of Na plus going into the cell, right? For a microsecond, pretty small. And so we're gonna have this giant flood because it really wants to go in the cell. And so your potential, your membrane potential in the cell is going to shoot up. And then we're gonna hit about negative 30. We're gonna explain why it does this. It's gonna go back down. It's gonna actually dip below the resting potential and go back. So this is an action potential, okay? This is depolarization. Anytime you go away from negative 70, it's depolarization. And it's opposite, this, right? This is below, this is hyperpolarization. We're going back, right? Okay, so we have Na plus come in. This is a voltage gated pump for sodium. And then we also have a voltage gated pump for calcium, or not calcium, potassium. These are very slow to react and very slow to close. So When this opens up, so does this. This starts to open up, but they're slow. So they won't get to it. Like these close around right here, okay? All right, we got 1, 2, 3, we're just gonna call this 4, 5, 6, we'll just call this 7. Pretty simple stuff. So we have potassium is going to open up, right? But pretty slow, way slower than this. It reacts very slow. And you're going to get potassium, oh my, I'm raising it, going out of the cell, okay? So we are hyperpolarizing this. These will close right here. This ball will go right here. It'll close this off right about here. And then we're hyperpolarizing. And we'll hit here, and we'll go down, 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 down. These are, remember, they're slow to close. So it takes a while for them to close. So we're gonna actually go below our resting membrane potential, and then we're gonna plateau back up as we hit equilibrium. And so that is kind of how an action potential works. We've got 2 different refractory periods. So we got relative and absolute. So absolute refractory period, about right here. So this is an absolute refractory period. And then this right here is a relative refractory period. Okay, within this period, we cannot have any other action potential at the same time. You cannot have an action potential in here because we're already having one. But here we could have a stimulus hit us right here, go hit up again, and suddenly we're in action potential again. So relative refractory period, you can have action potentials again. Let's see here. And I think that's all for action potentials. Hopefully I did it pretty well. Oh, we were gonna talk a little bit about calcium. I forgot about that. Okay, so with calcium, what it does, so Ca++, somehow, so we had that little gated channel, right? We had that gated channel. Let me just make sure I'm still on camera. Okay, we're still good. Okay, so we have this gated channel, and the spring, I forgot to explain the spring, but there's a spring, and as we lose Na+, which holds down this spring, it'll spring out and this will open up, okay? With calcium, it actually gets in the way of here and can bond with this, creating it much harder to create an action potential. So with the threshold, right, it was at -50. If we had a lot of calcium, our threshold would actually be up. But if we had hypocalcemia, so hyper would go up, the threshold would go up, harder to have an action potential. Hypo would bring it closer, so you could have it pretty close to having an action potential. Every time you got a stimulus, it would go. Yeah, okay. Okay, let's go to capacitance and length constant. We're going to just kind of explain how neurons work just a little bit. So we're going to have a neuron. It's going to be a big neuron just because we have myelin. And then we'll just go like that. That works. Okay, this is myelin. They call it the myelin sheath on neurons. And so this is kind of what we're talking about with action potentials in here. Okay, so we're going to have some pumps. Right, it's gated. We're going to have some more over here. So capacitance is the amount of charge to volts. So It's kind of weird, but remember how we're talking about membrane potential, resting membrane potential. Well, that's what we're actually talking about here. So we're gonna have, right, we're gonna have negative, 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 negative. And because this membrane, right, let's draw it bigger for you, right, we got phospholipids, blah, 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 right, but we have negatives up here, positives in here, and they're kind of close together, which allows them to have less repulsion, okay? This is important. Repulsion, because we allow them to have less repulsion to each other, we can actually fit more together, right? Because they're giving their negative or positive to each other. And this is capacitance, okay? So if we want to have less capacitance, we need to have less charges together. So that's on this portion, okay? But on the myelin, we're actually gonna have, let's just say 3, okay? But this is because our propulsion is much higher, okay? Does that make sense? Same thing with these, okay? Because we're not close together. So we have less capacitance, we have less, I'm pretty certain, give me a second. Yes, okay, sorry. So we're gonna have less capacitance right here, okay? Capacitance. Okay, so we have less capacitance because we have less positives and negatives. This is more capacitance. Okay, length constant, we're talking about how far, okay, we're gonna explain this a little bit different. So we have these pumps, right? They're gonna open up. We're gonna get a flood of any plus coming in. Okay, this flood of pluses, as Brother Shaw explained, it creates this bwang, or I kind of like propulsion, I don't know. This signal, right? That can affect these and actually open up these channels. It can actually create this channel to open up and make another bwang or propulsion. And so when we're talking about length constant is effective on how powerful this electrical field or something like that is. So the less it interactions with other things that it has, the better. So if we had let's just say, we're gonna get rid of this. Let's just say we had a neuron without myelin and it was smaller, okay? Negative, negative, positive. You get the gist. But we're gonna have more, our length constant will be less because we're having more distractions, more pumps, right? We have lots more pumps here now that are in our way. And so length constants involves RM. So RM is membrane resistance. So basically it's saying how many of these pumps do we have at that moment. So if you're within the myelin, you're gonna have a lot of RM, right? Down. But because this is such a wide thing, which is Ri, its internal resistance, we're gonna have less internal resistance also. Internal resistance is like, say if we had like a proteins in here, if we had a protein in here, right, it could block that pretty easily. But in here, because it's wide, you're not gonna get blocked as much. So this Rm is important to our length constant. Length constant is this symbol, and it equals the square root of Rm over II. So if we have less of that, it's going to be a better length constant. Okay. Yeah, I think that's about it. I'm not gonna lie. I think I'm done. Basically, myelin is a blessing. Makes everything faster. It also increases the speed of that belong as it goes along. But I think that's everything.